hotspot version. Then we talked about spatial aggregation and how this like modifiable areal unit problem kind of affects a lot how data actually like appears if we bin it according to some spatial binning algorithm. And we talked about this example of gerrymandering, and I just recently posted an article from today in the New York Times that kind of shows the effect of gerrymandering between the 2016 and the 2018 election. So if you read the news, you will have read that Pennsylvania had a court decision that it was like unconstitutional to gerrymander the districts for congressional elections on a partisan basis, and the court found that this was actually a partisan map. And so let's take a look at the 2016 map here. Look at like Philadelphia and Pittsburgh are small districts, and actually Democrats won Philadelphia by a margin of 80 points. Just imagine a margin of 80 points. And what that resulted in is that the Democrats got 46% of the votes for Congress, but only 5 of the seats, 5 of 18 seats. And so that's because of the gerrymandering. Like you see that the Republican Party had a lot of like tight wins, and the Democratic Party had mostly like lopsided wins. In contrast to this redrawn non-partisan map, we see that we have, in this case, 55% of the Democratic vote going to 9 seats. So it's not perfect, but it's a much more reasonable map. And we can see that the Democratic margins in Philadelphia now that include some of the suburbs are not 80% anymore, right? They're like plus 18, plus 27, plus 26, and plus 58. Still quite a margin. Because still people naturally, let's say, the Democratic voters tend to cluster in cities, but this map is clearly fairer to the average voter. And then we talked about that this is of course also an issue in Utah, so like Salt Lake City is exactly sliced up such that the liberal city of Salt Lake City is like lumped in with more conservative districts. We talked about Voronoi diagrams that are like a useful way of partitioning spatial areas, so that given a set of locations, for which area is a location the closest. And so this is a map of Voronoi this is a map of the world with an overlaid Voronoi diagram that visualizes the distance or from where you go to the closest airport. And Voronoi diagrams are also useful for interaction. So you can actually, like by overlaying a Voronoi diagram in the background for picking, we can actually leverage like the space that is closest to a particular piece on, for example, a line or in a scatter plot to pick that particular point, and then we avoid the problem of having to pick very tiny elements on our screen. And then we started to talk about clustering, and this is where we'll continue today. So as I said, clustering is a really important algorithmic complement to what we do in visualization. The idea of clustering is to classify items into similar bins, based usually on some similarity measures like a Euclidean distance, a Pearson correlation, a Chebyshev distance, or anything like that. And I like to distinguish, and you could argue about this, but I like to distinguish partitional algorithms, hierarchical algorithms, bi-clustering algorithms, and fuzzy algorithms. And we'll take a look at examples for partitional and hierarchical ones today. Just remember, partitional algorithms provide a discrete set of bins, so where every point is assigned. Hierarchical algorithms produce a similarity tree that we can kind of cut interactively, so we can kind of like manually refine, if you want to, the number of discrete clusters. Bi-clustering clusters both dimension and records simultaneously, and fuzzy clustering allows the occurrence of elements in multiple clusters, so we really have more like a probabilistic assignment to a cluster for each of the data points. And for visualization, we can use clustering to order things, for example, for pixel-based techniques like heat maps, to brush things when we use geometric techniques, and especially for aggregation, and that's kind of the main point of this lecture. And the rationale behind why we use clustering for aggregation is that clusters themselves are more homogeneous than the whole data set, so we can reasonably abstract the elements within the cluster and represent them with a summary visualization, which is likely to be more faithful to the overall trends in the data set than if we just took some arbitrary partitions or an overview of the whole data set. So I showed these examples here, but I'm going to skip over them. And then we started talking a little bit about k-means. And so the goal of, like, who's heard about k-means? Everybody, yes. Probably the most famous clustering algorithms out there. Who knows how it works? Okay. A couple of people, so there's a point of my lecture here. So the goal of k-means is to minimize the aggregate inter-cluster distance. So what we want to do is to find the total square distance from a point to the center of its cluster. For Euclidean distances, this also corresponds to the variance. And we can also use this to measure how internally coherent clusters are. So what we have here, like x in this example, are the data points. Mu is the centroid, and we kind of like measure the square distance between the data points in the cluster centroid, and we want to minimize this function for all points in all clusters. So the most famous implementation of k-means is Lloyd's algorithm. So the input here is a set of records from x1 to xn and a k. So k-means, as in the name, needs a parameter k, and that's something that you as a user have to specify. That's kind of one of the weak spots of k-means, that I have to know how many clusters are in a data set. And so the algorithm works as following. You pick k starting points as centroids, and these you can sample those from your points. You can randomly pick them, for example, but we'll talk a little bit about which strategies you could use to pick those centroids. And then while you haven't reached the convergence criterion, for each point, find the closest centroid, then calculate the distance between this point and the centroid, assign the point to the cluster defined by the smallest distance, and then for each cluster compute a new centroid. So that's kind of like the two-step process. Like first, find the closest centroid for each point, and then update the centroids based on the points that are in the cluster. And then you repeat this until convergence. And don't worry if you don't get this right now, I'll give you an interactive example. Repeat until convergence, and so convergence criteria could be like no point has changed cluster, or the distance between old and new centroids is below a certain threshold, or we have reached a number of max iterations. All of these are valid convergence criteria. Okay, so how does this look graphically? So here we have the squares here are data points, the circles here are centroids, and we've picked the centroids here arbitrarily in space. We actually haven't picked specific points. So we have an initialization, and so how many clusters would you say this data set has? 3, right? So the 3 squares at the top left, top right, and then this U-formed squares at the bottom. Okay, so the first step here is we assign this cluster. So what are the points that are close? Like for each point we find which centroid is the closest. And we see that for the point here at the top, this centroid is the closest. For those 2 points here, the green centroid is the closest. And for those points here, the blue centroid is the closest. So that's the first step of the algorithm. And now we update the centroids. So we essentially, we look at what is the position that minimizes the distance of the centroids to its current members. And we see that because we have only a single data point in the red cluster here, the cluster centroid now overlaps completely with our data point. For the green elements, we see that our centroid moves down a little bit. For the blue, we see that it moves inwards a little bit. And then we reassign the points based on distances. So we reassign the points, and then we keep iterating and iterating, and it looks like that we are likely to achieve kind of the clustering that we were hoping for in this simple example. So here is an interactive piece, and I kind of like this, and there is going to be a couple of things like that today. We will be using visualization to explain some of these algorithms. And that's actually also an interesting application of visualization to explain algorithms or mathematical concepts. So like you get 2 for 1 today. We'll pick, I'll choose the centroids here. I'll use a Gaussian mixture to initialize my data points, and like this is obviously 3 clusters, right? And so if I pick my centroids to be, let's say, here, here, and here, and then I do this thing, assign the points, update the centroids, we're done. Okay, so that was kind of easy. Now let me choose again. I use the same model, and now I do like a stupid initialization. Let's see what happens now. We see that we have actually like the 2 bulk, those 2 like point clouds here are now close to the green point. And so what is going to happen when I update the centroids? The green centroid is going to move here, and then the red and the blue ones are going to move into the middle of those clusters. And so if we can continue updating the centroids, we will see that we actually have found an initialization that arguably does not result in a good clustering result, right? So we have a problem here. Like this is clearly not an ideal result. So maybe you could argue that I have really adversarially chosen the initialization point, so I could do a better job. So let's try random. And now I'm like letting the algorithm add the points. Well, I'm not very confident that this is going to, well, it works out. Yeah. Let's try this again. Oh, sorry, now I picked too many centroids. That's the other piece, right, choosing the K. Okay, so, yeah, so it's not that bad. But there are cases where this is not going to work, and of course this is a very simple example. And so what could we do to like better initialize our seed points, our centroids? Any ideas? Yeah?
You could use one of the actual data points as your centroid.
Yes, I could pick actual data points, but do you think that's going to solve it completely? Well, completely, I don't want to say that, but picking actual data points is a good approach. There's like a little twist on that we can take that makes it even better. That's called the farthest point initialization. So I pick my first point at random, and then for my second point, I find the point that is the farthest away from that, and put the new centroid there. And so now I'm adding the centroid to the farthest point, and then I do, again, what is the farthest point from either of those, and that's now my added centroid. And so this is an initialization algorithm that is likely, or more likely, to give us like good results. Okay, so it means it has a benefit that it's super fast, and if you know the number of k, it's a really decent algorithm, given your data has certain properties that I want to talk about later. One of those properties is that we have, like, I gave you these like Gaussian blobs, which is kind of the ideal, the ideal data type for k-means. But if we do things that are a little bit more complex, and this is an extreme example here, the pimpled smiley, like a human, how many clusters are there? 4, right? So what are the clusters?
Eyes, mouth, and the outline.
Exactly, eyes, mouth, and the outline. Do you think k-means will ever get that?
No.
Yeah, so it's really tricky for k-means. Like I have 4, and then I click on go. And so you can see that basically k-means does not do well with this like circular structure, right? It kind of like assumes that clusters are in this point cloud. And so there's other algorithms, and we'll talk about one later, that actually does a good job at these kinds of data sets. So the other thing is, of course, choosing k is a big problem. Like here I have 2 examples where I have chosen k as too small and k as too big. One approach, if you don't use k, is to simply run k-means a couple of times with different k's and then use some kind of like measure for cluster for cluster quality to evaluate which of the k's is ideal. So that's one approach of doing that that's actually widely used. As we kind of saw already, that Lloyd's algorithm doesn't find a global optimum, it finds a local optimum, and it depends a lot on the initialization of our point, but it is very, very fast, as I already mentioned. And so we have the issue, like this pimply phase was an extreme example, but even like these two half moons here, or these kinds of clusters are not completely like uncommon, right? So we have these linear trends, but k-means is also bad at picking up on those. K-means also doesn't do a good job on these kinds of circular clusters here. So you will see like that's similar to our smiley face from earlier. It kind of like assumes a continuous cluster. And then unequal cluster sizes are also problematic for k-means. So here you could argue whether these are 2 or 3 clusters. If we initialize it with 3k, with a k of 3, we get this kind of like not very good assignment. Okay, so the second type of clustering I want to talk about is hierarchical clustering. And so there's 2 types here, agglomerative clustering and divisive clustering. And I'm going to like skip over divisive clustering, but the idea of divisive clustering is I start out with everything being in one cluster and then continuously split. Agglomerative cluster starts out with every element being in a separate cluster and then merging. Okay, so this is something I want to do on the whiteboard here. I'm going to draw this roughly. So I have nodes A and B. Then I have C and D. And then E and F. So this is kind of like the space where they're in, and then in addition to that, I'm going to like do a table here that I'm going to use to build up our dendrogram of our tree of similarities. Okay. So the idea of agglomerative clustering is this kind of like iterative merging of clusters. And so the first step in the algorithm is to identify the 2 closest clusters. And the 2 closest clusters in this example here, E and F. So what we do is we say these 2 are now one cluster. And then we draw an arc here between those 2. And in the height we encode the distance. So they are very close and hence the height is very low. And from now on we don't treat E and F as separate clusters anymore, we just treat it as one cluster EF. And for the purpose of this example, we'll say that like the position right in the middle of that is what we use to make our comparisons going forward. Now the next step is A and B are our second closest. So we merge those 2. We add, like this is a little bigger, we add that here, and then we say, okay, the center of those 2 is also right here in the middle. And now we have 4 clusters left. 1, 2, 3, 4. Next, we merge the next 2 closest clusters, which are C and D. Okay, and now we have C and D, which is a little bit higher. And again, we have our centroid here. And now we need to start like merging our combined clusters for the first time. And like, I don't want to, like, it looks like here that these 2 here are closest. So I'm going to like essentially connect them. And then our new centroid is going to be here, and that's a fairly big distance. So we have this here, like that. And then in our last step, we merge those 2 here. Okay? And that distance is also fairly big. So we have something like that. Okay, and that's kind of like all there is to agglomerative clustering. And now I can basically cut this dendrogram wherever I want, and then I have a discrete number of clusters. So if I cut it here, I have 3 clusters, A, B, C, D, E, F. If I cut it here, I have 4 clusters, A, B, C, and D separately, E and F. Is that clear? Okay. So my assumption here was that I used the center of the points for merging those clusters, but that's not the only way to merge those clusters. These are called linkage criteria. We have a couple of different ways of defining them. What I've used is average linkage distance, but there are other ones. There's like the maximum linkage distance, that the two elements that are apart the farthest, or minimum linkage distance that includes the closest two elements, or the centroid distance. So all of these are possible linkage criteria, and as so often in clustering, trying out different parameters, trying out different algorithms even is usually a good idea, and so these have benefits and drawbacks for certain cases. So how can we use this in visualization? Like this is super popular when we clustered biological data. Like heat maps of gene expression data is actually where this idea first was really widely popularized. And so this is an implementation that we did that has like this a multi-level hierarchical focus and context view where we have clustered here the rows in this very large heat map, and these two others are just pullouts. And the cool thing about this was also that you could dynamically adjust your dendrogram cuts and get a different number of discrete clusters. So here's a short YouTube video that demonstrates it. So this is an unclustered data set right now. It's not completely random, but it's not a, let's say, it's definitely not a good clustering. This is just adjusting some color maps. And then we can actually run, like this is now completely unclustered. Now we can run like a hierarchical clustering algorithm. We use Euclidean distance as our distance measure, and we get a fairly a clustering result that looks quite well immediately. And so we can use these like different levels of details. And now we do the dendrogram cutting, where we kind of dynamically refine the number of clusters. So that's a really powerful part of hierarchical clustering. And we've actually seen this before. If you remember this idea of hierarchical parallel coordinates, that we kind of like take a data set and use a hierarchical clustering and let the user choose dynamically how many clusters they want to represent in a parallel coordinates plot. Like here, starting out with a single cluster, then going to 4 or 5 clusters, and then like to something that I would say is clearly too many clusters to make sense in this particular plot. I did. Yes. I also want to talk about dbScan. So who's heard of dbScan? One person. Okay, so dbScan is another like super popular clustering algorithm, and it has a different idea than k-means. dbScan stands for density-based spatial clustering of applications with noise. And so like noise is an idea that k-means doesn't really, like the default k-means at least, doesn't really deal with, but dbScan assumes that our data sets are noisy and we shouldn't try to assign every single point to a cluster. The idea behind dbScan is that clusters are dense groups, so that points that belong together in a cluster are also close to each other according to some distance measure. You do dbScan, you have to use 2 parameters in dbScan, and epsilon. The epsilon is a measure for, like, if a point is within epsilon to an existing cluster, then you consider it as part of the cluster. And the other parameter you have is minimum number of points. That kind of like gives you the number of the smallest clusters. So if you look at this pimply face here, you could say that the pimples are actually outliers. And by appropriately initializing dbScan, we can actually see that pattern. And so this website also has this cool visualization for dbScan, and trust me that it works just as well for our like Gaussian blobs. But now the hard case here is our pimply face. And this here is just an illustration of the epsilon. So I can change the epsilon, but that's not going to be that important when I have initialized it. And now I'm clicking on go. And you can see you start somewhere randomly, and then you, for every point that you added, you kind of extend the contour of things that you consider to be part of the cluster interactively. And so you keep doing that. And so you can see how this now winds its way by means of connections based on our measure of epsilon across such a complex structure as the outline here. And if you give it a minute, we'll see that it kind of like reaches the point, and then if it doesn't, like if the next point that it's looking at isn't actually close anymore, it like jumps on to another piece, and now it looks at all the dots that are close to the mouth, and then the eyes, and treats the rest of them as outliers. And that's how you kind of like arrive with this nice clustering result. So what could be a disadvantage of DB scanning? Yeah?
Seems like your epsilon is pretty important to get right. If it's
Yes.
too big, you'll have, yeah.
The epsilon is really tricky to get right. It's super nice, of course, in 2D, right, when they can visualize a sphere or like a circle on the canvas. But in a high-dimensional space, getting the epsilon right is tricky. Other drawbacks? Yeah.
Seems like it could be computationally expensive.
Yes, that's one major drawback. It's very expensive compared to k-means. It's not terribly expensive. Look, worst case is n squared, but average case is n log n. But k-means is definitely faster. So yeah, those are two essentially partitional algorithms that you definitely should keep in mind. Okay, let me jump back. Okay, so the last section of the aggregation lecture is dimensionality reduction. So the idea, like we have had this design critique where we use dimensionality reduction, so you should already have a fair idea of what dimensionality reduction means. And so the idea is to reduce high dimensional data to a lower dimensional space. And that's usually for the purpose of visualization. So that I really can see my data, that my high dimensional data set in a lower dimensional space. And what you want to do is you want to preserve as much of the variation as possible, and then plot this into a lower dimensional space. The classical example for dimensionality reduction is PCA, principal component analysis. That's a linear mapping, and what we get are principal components. You can think of these as new dimensions, where we have a linear mapping by the order of variance. So if we have a blob like this here, we have, and look for two principal components in 2D space, that kind of does make sense. The first principal component is essentially this axis here along the blob, and the second principal component is this axis here in the blob. And so this axis here captures most of the variance in our data set. Here's another example of algorithmic visualization. So we start out with a 2D example. Here we have a data set, x and y, and these points. And then the red and the green axis here visualize our first and second principal component. And so what's the first principal component in this plot here? Or like this. Kind of like this line. So this is very obvious. And so how good is the first principal component at capturing the variance in this data set? Pretty good, right? And so you can see that here, now we plot PC1, the first principal component, on the x-axis, and you see that it, there's a lot of variance on that axis. The second principal component here, orthogonal to that, captures a lot less variance. Of course, the changes, I can interactively manipulate those points here. So if I do something like that, our first principal component still captures most of the variance, of course, but it's not as clear of a picture if I only looked at this in 1D. I'm kind of missing an important piece of the data set already. Here's a 3D example. So you have the 3D point cloud, and you can also easily calculate the PCA for a 3D point cloud like this. And so here we see for the 3D point cloud, this projection basically captures the first the first principal component and then the second principal component. And you can see that in this example again we capture a lot of the variance in our first principal component already. But of course this is lossy, right? So we don't have all the data in here anymore. In the example here, where we have as many dimensions as principal components, this is not lossy. But in this case here, of course it's lossy. Here's a 17-dimensional example. And the data that we see here, let me zoom in a little bit, are like food preferences across the countries in the United Kingdom. And we have England, Northern Ireland, Scotland, and Wales, and things like alcoholic drinks, cereals, fresh fruit, potatoes, and so on. And so if you look at this chart, which of those is least like the other? Which of those countries?
They look pretty similar.
Ireland, here? Yeah, so if you look closely, we see that Ireland eats a lot more potatoes. And that we have less fresh vegetables in Ireland than in any of the other states. And so we can do principal component analysis on a data set like this. And then if we just look at the first principal component, we can see that Wales, England, and Scotland are kind of like in one group, and Northern Ireland is on its own. If we look at this in 2D, like with two principal components, this is the result. And so I would say fairly accurate representation of this data set. So more generally, another approach is a multidimensional scaling. I don't want to go into the details of multidimensional scaling, also because there's many different approaches to do multidimensional scaling. But here, the idea behind multidimensional scaling is that it works based on projecting a similarity matrix instead of the raw data. So the questions that you have to answer if you want to use multidimensional scaling is, what is your similarity, how do you compute it, and then how do you project the points? Both of those. And this is actually fairly popular for text analysis, and this is kind of the example that we looked at last time when we had the philosophers and their relationships. The problem with all kinds of dimensionality reduction is, of course, that our 2D projection of, or our 2D scaling of high-dimensional data sets is never perfect, right? So this is what's called the curious case of petroleum engineering in a paper. So here we have an MDS plot of topics of dissertations published by Stanford departments. And what this looks like is that petroleum engineering is actually more like neurobiology than it is like mechanical engineering. Which doesn't seem to make a lot of sense if you think about those subject areas. And so what that is that this is really just an artifact of the projection technique. And so they have suggested an interactive technique to address this problem here. And this is like old enough to be Flash, so I have to allow that. Okay, so now instead of doing like a 2D projection, I actually basically click on one single subject. And now, of course, the distances here are faithful for like the relationship between electrical engineering and these other subjects are now accurate, right? So this is, of course, not multidimensional scaling anymore. This is basically just a similarity, but you could imagine something like this combined with multidimensional scaling. And I can change this, so let's look at computer science. It's very similar to electrical engineering. We see civil engineering is also fairly close. If you look at, say, applied physics, we can see that physics is close to applied physics, and electrical engineering is somewhat close to applied physics as well. So this makes sense, and of course this is noisy. This is text data, like real dissertations from these departments, and they have also faceted it by years, so that you can see what the differences, what the trends are over time. And of course, like this is like a smallish data set, so I wouldn't draw any general conclusion about the similarities of these fields. And so, like, these kind of artifacts of dimensionality reduction are kind of a problem. And so this paper here addresses that by making these artifacts very explicit, and I kind of want to show this video.
Hello. In our paper, Probing Projections, we describe a set of interaction techniques for analyzing dimensionality-reduced datasets. In this video, we're going to demonstrate them to you with the prototype web app we built to test them. To the left, you can see the projection. In this case, it's a dataset of OECD countries, reduced from 8 to 2 dimensions using multidimensional scaling. On the right-hand side are panels containing settings for the projection, displays of predefined classes, user selections, and clusters, as well as a list of all the dataset's dimensions. We'll walk through these individually. Let's start with projection. To examine a sample, you hover over it. For example, let's examine what makes Turkey such an outlier. Hovering over a dot displays a tooltip. For each dimension, it shows Turkey's values as well as how it compares to the rest of the dataset. From top to bottom, you can see the various dimensions. Left to right, there are the absolute value, the standard deviation, and a graphical representation of the deviation. These values are color-coded to quickly show where they deviate from the rest of the dataset. Instead of comparing Turkey to the whole dataset, let's compare it to just a single other country. To do this, we first select Turkey by clicking, and then hover over a rectangular surface in greater depth. Again, different numbers of clusters and the differences between them. Clusters can be analyzed just like selections. They can be compared with other clusters or with user selections. For later reference, they can also be named and saved as selections. We've looked at the samples of the dataset. Now let's take a look at the dimensions. A list of dimensions is available on the right-hand side. It provides spatial and numerical representation of each dimension's distribution. The spatial distribution is displayed as a heat map, showing where values fall on the projection. These heat maps can be used to get a general spatial overview of the projection, visually map dimensional values to clusters, or to compare different dimensions to each other. On hover, the heat map is also overlaid onto the projection.
So this shows you basically where like
There are two
points
ways
of
to
high
visualize the
value
quantity.
in one dimension end up.
Displaying a dendrogram and displaying approximation errors directly. The dendrogram is mapped onto the projection, with thicker lines indicating closer nodes lower in the tree. It's also a good way of visualizing the quality of the projection.
So this is kind of like an interesting approach, right? Because now they're superimposing the dendrogram of the closest points based on the hierarchical clustering algorithm on this projection, and therefore we can see very clearly if 2 points that are actually close in space to each other are not connected by an edge, then this is an artifact. What's the downside of using something like this with the dendrogram in the background? Of course, it's going to look quite cluttered if we have a lot of data points, right? So this is kind of like good to build an understanding of what does dimensionality reduction do. But for larger data sets, all of these techniques are slightly tricky. Okay, so the other thing that you probably heard about is t-SNE. Basically, everybody's talking about t-SNE as the way of looking at data that you otherwise would use for machine learning. And t-SNE is a t-distributed stochastic neighborhood embedding, or neighbor embedding. And the key idea about t-SNE, and I'm not going to go into the math at all, but it's a nonlinear algorithm. And the idea is that it applies different transformations for different regions to account for these kinds of clusters. Interestingly, people ignore visualization wisdom of not using 3D scatter plots when they do t-SNE data. So here we have our MNIST digits. I assume, like, who doesn't know what the MNIST digits are? Okay, so MNIST digits are these like handwritten digits, and like one of the classic classroom examples to machine learning is, because we have ground truth labels, is to write an algorithm that correctly identifies these handwritten digits. And you can use t-SNE to project the data that we have from those handwritten digits, and the labels here are the color codes. And so you can see that we have a pink cluster here, and those are in fact digit 6. And then if I click on one, you can see the examples that are given for that particular example, for this particular data set. And then we have one here that at least looks like it's on the border of this cluster that t-SNE has identified here for 6. And if you look at the specific image, we get a sense why this is not considered to be like among the most representative examples of number 6. So here we have the digit 1, and then here we have an outlier for 1. That's actually a digit 3, but it's actually quite far from our typical digit 3, right? And you can do this with any kinds of data, of course. And t-SNE is, like many of those algorithms, quite sensitive to parameterization. And so this is a nice article by the Google Picture team on this interactive machine learning platform, distill.pub, that kind of lets you explore and get a little bit of a sense of the parameters of t-SNE. And so you have the perplexity and the epsilon here. And if I modify those parameters, it kind of like reruns the algorithm. And so one of the things that like these guys, this is Fernando Viegas and Martin Wattenberg, they always argue if you have any algorithm or anything like that, one thing you should do first is to look at what does your algorithm do to noisy, to random data. And if your algorithm suddenly produces results, like clusters, clear clusters for random data, then this is slightly off. So I encourage you to like play with this. They have, like all of these are interactive, you can click on them, but you can see like our original data set, and these are always simple examples, right? We have 2D input, and then we use a dimensionality reduction technique that doesn't actually make sense to use in 2D because it's just perfect as we have it in the original data set, but that kind of is only to help you understand what the parameterization does. And so if you play with perplexity, like a perplexity of 2 results in these kind of like very disjoint sets. A perplexity of 5 or 30 or 50 looks good. A perplexity of 100 doesn't tease those apart anymore. And there's many other examples. They also have an example for random noise. And so here, I guess you could make an argument that with this perplexity, it looks like your random noise has these like little clusters, when in fact it doesn't really. Okay, the last thing I want to talk about multidimensional scaling is a really cool idea about using temporal data, how to visualize temporal data with multidimensional scaling. And so think of examples where you have a data set where you have multiple multiple snapshots, like the state of a Wikipedia article, for example. You can imagine that an article like Palestine or religion or anything like that will likely see some edit wars going on, right? It's like one person thinks this should be in the article, the other person thinks this should be in the article, and they're continuing to revert or change things. And so what this technique does is takes these snapshots and then it projects them based on their similarity in 2D, and it also connects them with a line based on the time. And so what we get then is, like for Palestine, here we have let me get my pointer. Here we have quite an intensive, or here we have an edit war essentially going on. So you see that there is like a quick alternation between these different states in quick succession. Interestingly, there's also a slight edit war for chocolate. But this is, of course, you could do this not only for Wikipedia or text data. Here is like a pattern, like a time curve for global cloud circulation. And guess what the cyclic pattern here is? It's the year, like 1 year essentially happening. And so this is just a neat idea. If you have, you could also use this, for example, for time-varying networks, and then do some kind of like similarity analysis between time-varying networks and spot where has a network changed a lot over time. So any questions about aggregation, dimensionality reductions, clusterings before we move on to set visualization? Yeah?
What algorithm did this again?
They use a multidimensional scaling, like just a basic MDS on the text data. I don't know exactly what parameterization or which version, or this is the link here. When I get to the slides, there's a paper where that you can look it up. Yeah.
So when you're doing dimensionality reduction and say like you know how we recognize like components of trends, say for example in the 3D, does that new axis, does that give you different, like does the axis kind of change if you scale to that, like when you like normalize to that new axis, like what is that new axis?
So in the example of principal component analysis, you have one, let's say for the first principal components, it kind of fits one axis into your high dimensional data set, and that measures the variance along that one axis. And if you have like a very clear linear trend, then this one axis will capture all the variance in your data set. If you have a nonlinear trend, it will not. Then you need more principal components to capture more of the variance of the data set.
Thank you.
Okay, cool. So now let's talk about set visualization. And so what do you guys think of when you think about set visualization? What's the first thing that comes to your mind?
Venn diagrams.
Venn diagrams? What did you say? Anybody say Venn diagrams? Who's heard of Venn diagrams?
Yeah.
Yes. That's how we learn about sets, right? Like that's what we have in like high school math. You draw like this is a circle, and then this is a circle, and there's two overlap, and therefore there's an intersection between those two sets. So I want to run a design workshop now. It's going to take us about 20 minutes or so. And the great thing about this is you can get a bonus point. And so what we'll be doing is I'll give you a data set, and you're supposed to design your own set visualization. So let's start out with like a problem statement. So here we have items and we have sets. So item 1 has A, item 2 has A, item 3 has A and B, item 4 has A and C, item 5 has A, B, and C, and so on. And so we could simply visualize this in a Venn diagram, and we would be successfully able to capture this relationship. This works well for 2 or 3 sets. What do you think will happen if I have 5 or 6 sets? It gets really tricky, right? And still people try to do that. This is a paper, again, a major Nature paper from 2012 that analyzed the relationship of the genome of the banana to 5 other plant species. And this is the Venn diagram that's actually in this paper. I call it the infamous banana Venn diagram. And so this is actually, if you look at 6-set Venn diagram in Wikipedia, you get this picture, but not with the banana. So they added this banana to make it like fit their paper topic. But this is actually one of the worst visualizations out there, and I think I showed this example before. And so why is this a bad visualization? So first we have, like, it's really like there's no proportionality of the size of the data set to what is actually shown on screen. So here we have a segment that has 1,151 genes, so that's kind of a very important segment in here. And then one next to it, there's another segment that's equally prominent on the screen here with only 40 genes. And then in comparison to that, we have only we have this gigantic segment on here with only 105 shared genes between those plant species. So it's really tricky to do more than 3 sets in Venn diagrams. And this is not an isolated incident. This has been fairly popular in like the last, in these genomic papers. We have like the mouse genome, the pine genome. This is the rat genome, I think. And so like we see a lot of those, and actually like we build a visualization technique that's supposed to address these problems, but now I kind of want to challenge you to try to come up with a solution for this problem. And there's many different solutions, and I'll give you a simpler data set than shared genes between species. We'll look at characteristics of the Simpsons characters. So we have Lisa, Bart, Homer, and Mr. Burns, and others. And we have characteristics such as they go to school, they're female. They go to school, they're male. They work in a power plant, they're male. They're evil, they're male, they like Duff beer, and so on. So all of these kind of attributes about those people. So what could you imagine are questions that we would like to ask on a data set like this?
How many people go to school?
How many people go to school? Yes. Another question.
How many people are all in the same sets that I'm in?
Exactly. How many people are in the same set that I'm in? Another idea?
How many evil people work at the power plant?
How many evil people work at the power plant? Or we could ask questions such as like, do people who are in school also go to school, work at the power plant? Or do people who are in school also like Duff beer? Or is there a relationship between an attribute like age and their preference for Duff beer? So all of these kinds of questions is what we could try to ask. And so what I would like you to do now is to work in groups of up to 3, get to know the data. I have a handout for you guys that I'll give you in a minute. And then create 2 rapid prototypes. Like spend about 5 minutes on each. One suggestion, first try to draw a Venn diagram. Just try it to see why this is not a great idea. And then write up your two designs in like a Google Doc or Word document. You need to make a PDF out of it. And then I've created a bonus Canvas Dropbox where you can submit this today by 5 p.m. And if you submit a reasonable solution, you get like 1 percentage point added to your grade. And then I'll show some of your solutions next time. And well, if we still have time after we do this, I'll show some of the solutions from last year's class. So, questions: what is the biggest intersection? Which set makes up an intersection? How big is an intersection? Does it work for more than 4 sets? Do attribute values correlate with an intersection? And like one tip that I've just from experience, I've seen most people always try to visualize every single person. Many of those questions can actually be answered without actually drawing Homer or Marge. You can like do this more abstractly, right? Like a Venn diagram actually, like you don't have to draw every single person. This is just like because I've seen it a couple of times. So now you get the handout with your characters and properties, and there's more instructions on there.
He said